We were reading through some of Valerie's fan mail. Valerie gets a lot of fan mail. I don't get any. But anyway, we picked an interesting one that I thought we would address now. So let's have Valerie open this letter. It says, "Dear Valerie, why transfer functions? Love, devoted fan." So we will answer this question today and answer Valerie's devoted fan's question. So now we're going to work on answering the question of why transfer functions. It's a great question. And we use transfer functions, and recall that we have been looking at the plant transfer function, so we've been using this P to mean plant, so the system, and it's the output over the input, the signals. And we've converted it in terms of S, so we're looking at the frequency domain. And this is valid, this model for understanding systems is valid for linear systems only. So everything we've looked at so far has been a linear system. So what exactly are we doing with this, and how can we use this tool? We're going to cover that in depth later, but I wanted to just talk about it right now so that you get a sense for why we're actually using the transfer function. So first, let's talk about S. So what exactly is S? So recall, S equals J omega. And I just memorized this, S equals J omega, always. And then what is omega? Omega is equal to 2 pi frequency. So it's the frequency in radians. So if you memorize these two equations, you can always kind of remember where it's coming from. And what we're looking at essentially is how the frequency affects the system. Okay, so let's just put these all together. So S equals J 2 pi frequency. So that's our expression for S. So you can just, if you're kind of confused about what S is, think back to what this actually is. So we're looking at the frequency, and we're looking at how it affects it we're going to look at the imaginary and real axis. Okay, so we have this S, still a little bit confusing maybe. Let's go back to one of our simple examples and look at how we can use this. Okay, so we're going to go back to our capacitor. I'm not going to redrive everything, but if you recall, if we look at the impedance of this capacitor, it's going to be 1 over CS, right? So, and if you don't remember that, go back to one of the earlier videos where we derived that. So let's think about what this is. So let's just plug this in here and kind of think about it. So 1 over C, and then S is, we're going to move it to the front, J 2 pi F. And so we can look at how frequency affects the system. In this case, we're looking at the impedance, so we can see how frequency affects the impedance. And first, there's two things that we can do here. We can look at how the impedance affects the magnitude of the signal, and this is essentially the gain of the signal. So we put a signal into our system, and we're going to see how it comes out. Does it have the same magnitude? Is it a lower magnitude? Is it a higher magnitude? So, but first let's kind of break this up. So first we can look at, this is Z, right? So we can actually look at the magnitude of Z, and if we look at the magnitude, we're not worried about the J. Another way to represent this is to look at the real and imaginary axis. So really what we're doing here, this J means that it's pointing directly in this direction, the negative I direction. Oh, sorry. It is going to be that way. We actually have to multiply it by J, and then we'll see that the expression actually goes to negative J 1 over C 2 pi F. So from here it's a little bit clearer that the J is actually in the negative direction. So if we look at this here, it's pointing down, so that's a J, and its magnitude here is 1 over C 2 pi F. So we can break it up into the magnitude and the angle of z. So here it would be negative 90, it's pointing downward here. And then the magnitude here would be 1 over c2 pi f. And we're going to do a lot more of this, so don't worry too much if you're not capturing it. What I want to focus on is actually the magnitude here. So if we look at a very high frequency, so let's write this here. Let's say that frequency goes, I'm actually going to write it here. Frequency is very high. We're looking at a very high frequency. It's going towards increasing, increasing, and increasing. If we take this expression, f towards infinity, we'll see that it goes towards 0. So 0, z, the magnitude of z, would go towards 0. And if we do the opposite, if we take f going towards 0, which is DC, no changes in the signal, just DC, then we see that this goes to infinity. So the magnitude of z goes to infinity. This is all the math part. If we think back to this capacitor itself, what this means is that at very high frequencies, towards infinite, our impedance is 0, and impedance of 0 here is effectively a short. So this is frequency going to infinity. And the opposite, if we take the frequency towards 0, our impedance goes towards infinite, which is essentially an open. So you think of it, frequency goes towards 0, we have an open circuit. And the way I like to think about this is if you have a capacitor and you put just a stable frequency over it, it's not going to do anything. This is essentially acts as an open and just holds the charge, holds the voltage. If we put a lot of high frequency into it, it's actually going to short and become like it'll become like a short. It has a very low impedance. So we can actually use this in a system now, which we're going to do in a second. So we just talked about how the capacitor reacts to different frequencies, and now we're going to look at the system and try to bring it back to the transfer function. So here's a really basic system again, and now that we've become more familiar with these systems, we may be able to see this as a voltage divider, and we can take the impedance of this and directly derive an equation. So let's do that. So we know that the output voltage here, and we're actually going to go directly into the Laplace domain, so we're going to do V out of S. The output here is just this voltage times this voltage divider here. So we'll do V in of S, and we look at the out impedances here, so it's this impedance plus this impedance. So we'll be general first. The impedance of the resistance plus the capacitor over the bottom part, so there is impedance of the capacitor. And we know that the impedance of this capacitor, like we just talked about, is 1 over CS, and then the resistance is the same as the impedance for the resistor. So R is just equal to R. So let's fill that in real quick. And we'll also see that we're already in the nice form. We just need to move VI over here, and we have the transfer function right here. So we'll do that as well. We'll move VI down. Okay, and fill in these transfer function values. So we have 1 over CS, then 1, we'll do that one first, over CS plus R. Okay, so, and this is not, it's simplified, right? But first let's do some analysis on it. So if we see this circuit and we say, how does it react when we have a very high frequency? So let's look at S going towards infinity. Well, we see that if S goes towards infinity, these are both 0, and so we're left with 0. So our total, this figure here, which can also be thought of as the gain of the system. So you're putting in an input, how much comes out of that relative. So we'll call this the gain of the system. So I guess we'll still call it, yeah, the magnitude of GP of S. That would go, because this is 0 and this is 0, this whole gain would be 0. Now let's look at the other case. So what happens if we have a very small frequency? So S goes to 0. And remember, S going to 0 is essentially the same as F doing the same thing here. So let's write them both. So if we have a very low frequency, almost DC, we plug that into here, we see that these dominate, so we'll actually get close to 1. So this becomes not important because these both go towards infinity. So the gain of the system goes towards 1. And this is the more mathematical approach to kind of analyze it. The way I like to think about this is at DC, this is essentially an open, remember, so DC, very low frequency, this is essentially an open, and the voltage would just go straight through. This would be essentially an open. So that's a gain of 1, it goes directly through, so that's the gain of 1 here. But if this was very high frequency, this capacitor begins to act as a short, and then the voltage, no matter what this voltage is here, this would be 0. So essentially the gain is 0, there's no gain. And so another way to think about this is that this is a low pass filter because it lets low frequencies through but filters out high frequencies. So that's how we use the frequency to analyze our system. So now from this expression, the transfer function, we can get a sense for how the system reacts to different frequencies. And going forward, we're going to look at more complex systems, but I just wanted to kind of talk briefly about this now before we really dive deep into it. So I hope that helps explain some of it. It might have been a little long-winded, but I hope it helps.
What? That's your answer, Valerie? Because? Well, it is a lot shorter than my answer was.